Good day. We will now get started with a very hot contemporary topic of neural network, which also introduces the basic idea of perceptron. We look at some idea of deep net which comes out of that, and one important algorithm which is called backpropagation algorithm. You have multiple hundreds of full fledged courses on this. So, what we are going to cover here is mostly motivational, elementary idea, and a feel for what is happening. What today people call machine learning, mostly using neural net, is approximately 75 to 80 years old, meaning ideas around this have been there, which now matured about 15 to 20 years back only. Okay. For many of you who have done digital logic, there used to be an interesting concept called threshold logic. Now, what was that? You had a logic gate with, let us say, inputs x1, x2, x3. You had an output function t, no, not output function, output function let us say y, and there used to be what is called a threshold t, which could easily be a minimum voltage or whatever it is when you realize it. The was that this would of course get added. So, x1 plus x2 plus x3, if it is greater than or equal to threshold c t, then output y is equal to 1. If this is less than t, output y was 0. This is very 50-60-year-old digital logic exercise. Of course, you can extend it to x1 plus x2 all the way to xn. You can make it even more interesting by having w1 x1 plus w2 x2 plus etc. wn xn, where you attach weights w1, w2, w3 in this case. So, these weights, weighted input, different weights are interesting. There is a saying called seeing is believing. What is seeing is believing? You give more importance indirectly higher weight. For what you see, compared to say what less importance as a lower weight, lower value. Weight is a real number, less importance to what we hear. This is actually found to be very valid while we drive. All of you have experience. You trust your driving more by what you see, and sometimes even you check in the rear view mirror. This is a fact in biology too. So, in biology or in human space, we give more importance to what you see, which means different attributes have different weights, W1, W2, Wn, not necessarily equal. Okay. This is in fact used today when you look at machine learning. Crudely speaking, machine learning is equal to knowledge of these weight values. That is it. Machine learning is almost like saying, can I discover the weights associated with various attributes? I will come to that. Okay. So, looking at threshold logic, now see the biological neuron. Of course, a rough or gross, or you can even call it a crude model. This is a crude neuron model effective for our purpose. This is called the cell body. These are termed dendrites. The long tail is called axon. These are axon terminals which end up being either end up directly or get connected to other cell dendrites. So, you have a cell body, you have dendrites, axon. These dendrites are where inputs to the neuron cell. There is this cell body which does the processing. The output is normally a spike which connects to other neural cells. This is the idea with which early perceptron was made. So, the famous person McClock and Pitts developed this. They called artificial neural net, which look like this. You have x1, you have x2, adds, generates a partial output, which has a threshold like theta, and the output y is 1 if x1 plus x2 is greater than or equal to theta, equal to 0 if it is less than theta. So, basically this looks like the standard input x, output y, a famous input output model which most system descriptions are familiar with. Okay. We will not go into details further of this, but if you can modify this a little, you can do standard Boolean gates like AND, NOT or OR. So, there was an attempt to look at Boolean logic circuit, circuits along the neural model. But we also know one thing. What is it we know? We know that for any more sophisticated computer like operations, we need XOR, right. So, you basically want a neural model for an XOR gate. With the above, it is not possible. So, this is one reason 50 years back this early work of neural network did not progress, it came to a halt. So, later work modified this, I will come to that later, but definitely there is a neural model for these. It is a good beginning. We will see more of this now. If you look at a more general structure, it looks like this. You have x1, you have x2, etc., etc. You have xn, you have a summer, we will call this the input side function g and the transformation side f, produces an output z where so what is g? G is equal to x1 plus x2 xn, right, which is sigma xi I equal to 1 to n. Now, f of some function z is equal to 0 if z is less than theta, equal to 1 if z is greater than theta, and this z is y is equal to f of g of x. This g of x is actually z. Okay. So, this will be 0 for g of x less than theta, equal to 1 for g of x greater than 1. In practice, something more interesting happened. This portion is also called the activation function. Activation function is how it transforms the input. The input is not directly fed, the input is transformed through an activation function, and you have elementary activation function like this, whatever the theta. You can also have activation functions like this, you can have activation functions like this, so on and so forth, depending on applications, context, etc. For example, all of them which have, even if you take a variable theta, all of which have non-zero values for theta less than 0 are activation functions which already work on memory. This has no memory, instantaneously it responds. For example, in the neural world, our current response is based on current input plus past input and responses. If current response is based on current input, which is pure causal, whereas current response is based on current input plus past input and responses, non-causal. This is human, very much human like, because many neuron behavior or we respond for the same question, we give different answers depending on who the person is. That is because we have dealt with the person in the past and we have a memory of that and we use the memory of that, and so whenever you want to involve the memory of the past, you need different activation functions. We will not go into this because it is very vast, very involved, but fair enough to say that you have so many different, for example, your locomotion, when you are walking and you find a pothole or something like this is the response. But when you go to eat a particular item in a restaurant or you meet your friend and all that, your current response depends on what you have interacted with him, how familiar, what nice things or what not nice things you have experienced. Okay? So, we will not go so much into the memory, and in this and the next few minor topics, we will not focus much on the activation function. For all practical purposes, you can assume this or a simple one like this all along, continue, but when you actually implement, you have to choose the activation function. So, basically learning is moving beyond logic gates. Logic gates are fine. Logic gates do Boolean functions, they solve an immediate problem, you can realize it in hardware, but there is no learning. Learning has two components. Learning has a memory, learning has an adaptation. Adaptation is an early sign of learning, and having all that in memory is what makes learning very strong. Okay. So, the perceptron model looked at learning in an interesting way. They model learning as weights associated with inputs. So, the perceptron model becomes even interesting. You have a input part which you can designate as G, a transformation part F, and output Y. The inputs were not arbitrary, they were x1, x2, etc. xn, but all of them were given weights W1, W2, Wn. You have an adder, so this part is sigma Wi xi I equal to 1 to n, weighted sum of different inputs. You experience this also in a working space. Somebody tells you to do something, you say I will do it or postpone it. Suppose the person who tells it is your boss, you immediately do it, which means the weight associated with an input influences your response. Okay. Many times we also have an input which is B. B refers to a value called bias. It could also be 0. You can also have bias term negative. Okay. Now, we keep using the word positive bias, negative bias, he is biased against me or he is favoring me. So, this is it, bias is there, and bias is conveniently used with a weight equivalent to W naught. Okay. W naught is B. Okay. So, we have a value x of 0 attached with that, call it bias which is W naught, and we always make x of naught equal to 1. So, that now you have the slightly modified version which looks like sigma Wi xi I equal to 0 to n with x naught always identically 1 and W naught equal to B. So, barring a discussion free of activation function which anyways transforms the input to the output, we now have the following condition. The y will be equal to -1 if sigma Wi xi is less than or equal to 0, equal to +1 if sigma Wi xi is greater than 0. 0 is the threshold, okay. Barring a theta, 0 can be taken as threshold. Now what is W? W is W1, W2, Wn, right, and X is 1, X1, X2, Xn. So this becomes Y is equal to -1 if W transpose X is less than or equal to 0, equal to +1 if W transpose X is greater than 0, with W naught equal to B. There is a proof, the proof is called perceptron convergence theorem. Okay. Please read this just to convince yourself that some learning happens associated with weights W0, W1, Wn. What is the learning? Learning is learning the input and it generates an output based on the activation. The next topic we need to discuss is moving little beyond perceptron, what one calls a multi-layer perceptron. How many? Multiple layers. So, the summary of what we have learned so far is that there is indeed a neural basis for learning, which was well understood, but there is a neural analogy. It may be crude, but crude or rough or even functional at most, not really a replacement for the brain neuron. Neural analogy in terms of Boolean or digital logic. We also saw that Wi, a set of weights I equal to 0 to n, in particular W naught is B, which is bias, and it can also be 0, bias can be 0. This weights some sense indicate learning.